Hello. Hello. I guess everyone can hear me. Am I audible or not? Yeah, thank you. So let's wait for another 1 2 minutes, 1 or 2 minutes, and then we'll start the session. So good afternoon, everyone. Good evening, everyone. So welcome to today's session of this. Just a second. Why isn't it going? Yeah. So welcome to today's session, and this is a problem solving session of uh, course titled as Sensors and Actuators, and this is the week 3 of this course. My name is Shomna Bhattacharya. So here's a brief details about me. I am currently pursuing my PhD in the Department of Electrical Engineering, IIT Jodhpur, and I am working towards development of flexible and organic transistors, specifically for neuromorphic computing applications. And previously, I have completed my bachelor's in physics and master's in electronics. And the basic class schedule is on every Sunday from 6 to 8. There will be a shift in the schedule as I'll be attending a conference, and that will be formally informed by the NPTEL team to you guys. And I'll also like inform beforehand. So this is the basic course layout. The first week, we have learned about the basics of energy transformation, that is sensors, transducers, and actuators. What are these things? What are the key difference between these, and what is the need of these things separately? Then in the next class, so in the next one, we have learned about the fabrication techniques used. What are the like required environment, like what is clean room, what are the protocols, how to enter in a clean room, how to maintain everything in a proper maintain a proper protocol inside this clean room. And there were several like do's and don'ts and these things. And separately, what kind of a techniques have been used to fabricate these sensors, like starting from the different kind of a deposition techniques like evaporation, sputtering, ALD, and these kind of a things, towards patterning techniques like lithography, mask aligning, and these things, and further etching and these things. So we have already learned a bit of basics of these things, but today we'll go more in depth towards photolithography. What is this, and what are the recent trends in sensor fabrication? Which kind of a clean room equipments have been used for these kind of a yeah. So the main outcome of this course is towards the so the for the first 4 to 5 weeks, it is kind of a knowing the basics of this techniques, and finally you should be able to handle these kind of a things. So if you were if you want to fabricate your own sensor that you have designed and everything, so you can go inside a clean room where you will have access to, obviously, but you will get the basic idea of how to enter a clean room, how to maintain the protocols and everything. You will know all these fabrication techniques, all these things, and how to choose which one is perfect for you. Do you need more accuracy, or do you need more precision and these things? So there are several different things, and how to design interfacing circuits. So how will you like interface your fabricated sensor with your total circuitry and everything. Then further you will move on to different material simulations like console multiphysics and gas sensor demonstration. So how console multiphysics describes your fabricated sensor performance and everything, how these kind of sensors are affected based on the environmental factors. So a total total view will be given upon you. And when you are going to fabricate your sensor and when you are designing your sensor as well, so you will have a complete knowledge of these. And then moving towards like Arduino based applications, and where can your sensor, your fabricated sensor be applied to and be a best suitable candidate for you. So you can also choose your materials, you can also choose your techniques. So like we are also discussing all the techniques, all different kind of materials. If you need your sensor to be flexible, or if you need your sensor to be long term like reliably perform. So like if you want it to be reliably perform over a long term, so you need these kind of a things. And if you need like for a biomedical application or something, you need a flexible one which decays over time, or which is like maybe based on any kind of a stimulus it decays, and these kind of a things. And further the final few lectures will be on CAD modeling of these different kind of sensors and these things. So there will be very few examples, and based on that we'll move towards that how these sensors have been made, and you can implement that on your sensor as well. So first you will design it and then fabricate it, and then you will interface it with your existing circuitry and these things. And the last one is towards like 3D printing and these kind of a thing. So these are advanced techniques. So like in the first things let me just brief it down a little. So in the first lectures what we are right now studying is that we are doing something called a subtractive technique. So what is a subtractive technique? So whenever you have a, let's say, a block like this, and you need to get a pattern. So if you are doing photolithography, so this is like this. So you need this pattern. So in photolithography, what do? You deposit all over this area, and then you subtract the. Okay, sorry. Let me change to this then. Just a second. Wait for a bit.
Is this one clear? So is it better or not? I have changed my device. Can someone confirm? Yeah, okay.
I was saying that, so in photolithography or any kind of deposition techniques and these kind of things, generally you use a technique that is subtractive. So what is subtraction? You know that, right? So you have a total thing and you need to eliminate most of the part to just get a specific design or something. So if you need a subtractive technique, then these materials will be wasted, right? Even if you have a very dense kind of a design and everything, there will be a huge wastage in this case as well. Now how to tackle this? The best way to tackle this is using a technique called additive technique. So in additive technique what happens is that
you directly use or you directly print a specific amount of material in a specific design. So what a printer does is that a printer doesn't like what do I say, like for an inkjet printer or a different kind of a printer, what happens is that it it drops some kind of a ink, and based on that it creates the pattern. The hand creates the pattern, not we don't need a specific technique like etching or something like that. But in case of a photolithography or something, you need to coat your PR over whole surface, you need to deposit your metal over whole surface, and these kind of a things. So there is a wastage of material which we are removing in these new kind of new generation of techniques like 3D printing or these kind of a things. So they are like the newer generation things that will reduce the all reduce the production cost, and also will reduce the wastage of materials as well. So these we'll also talk about these kind of newer generation techniques and these things as well. So let's move on to the like third week. So it's known as like trends in sensor fabrication and clean room equipment. So we'll learn mostly in this lecture, we'll learn most about this photolithography technique, that is the complete photolithography process, and what is the importance of each process steps and these things. Then we'll know a bit about the bulk and surface micromachining. And due to the previous class, so there was my network issues, and because of that we haven't been able to discuss previous week's questions as well. So we'll discuss that as well. So for this lecture, I'll try to reduce the this study portions a little bit. So if you have any question, you can ask me and we can discuss it later. So the first thing is that, so in photolithography, the first step is cleaning. So you will have a sample. You need to clean it first. So let's say you have a sample like this. So there are several kinds of cleaning techniques. So for normal conventional electronic things, so there is something called RCA1, RCA2, piranha cleaning. So these are different types of cleaning techniques we usually use to reduce, to remove any kind of a contaminant on the surface of the substrate. So mostly in these cases, this is a silicon wafer. So there are specific kind of a contaminants that can be easily removed with RCA1. There are several that can be removed with RCA2 and so on. Now, after cleaning this wafer, so in general what happens is that inside and liquid filled liquid filled what do I say, um not chamber exactly, but liquid filled beaker or something, we directly put our silicon wafer inside it and hold it for some time. Sometimes we ultrasonic it as well, and then we heat it to remove any kind of a residual solvent and these things. And so these kind of a things is usually done for silicon wafers. So there are several different kind of a cleanings as well. So for flexible substrates like plastic and these things, what we usually do is that, so they are susceptible to these kind of piranha cleaning solution or RCA1, RCA2. So in those cases, what we do is that we use this process called ITAM. So what is ITAM? First we clean it with IPA, that is isopropyl alcohol. So then after that we use TCE, then acetone, and further methanol. So these are used we usually dip it inside these kind of a solvents for 10 minutes, and then we heat it for 10, 15, 20 minutes on the hot plate, and after that we remove it with, and also DI is also used in between each step as well. So DI is DI water flow is put on these kind of a substrates, and they are cleaned completely. and after that the next solvent is used. So there are several different kind of techniques for flexible and like rigid substrates and these things. So these are like several different techniques. Then further, the first step, that is the like mostly like the cleaning is not exactly part of photolithography, but a cleaning step is necessary as well. So after that, the step is known as the spin coating step. So first we spin coat the PR. So in the previous class we have discussed about positive and negative PRs and these kind of things. So PR is spin coated on top of this substrate, clean substrate obviously. So there are usually for different kind of a PRs there is a specific recipe. So how much RPM you need to spin it for, how many minutes you have to spin it for, and these things. What should be the acceleration of the chuck and these kind of a thing. So for different PRs, there are separate like different combinations, and what is the optimized value of these things to get a optimum like thickness layer and these things. So this is the second stage. Then after that, so this is one of the unique stages that is known as the soft bake stage, or sorry, soft bake stage or pre-bake stage. So what does a soft bake mean? So in soft bake, what happens is that we usually give a very low temperature. So let's say 90 degrees centigrade for let's say 1 minute or so, and we just put the substrate directly onto a hot plate. So this is our substrate, and we directly put it on top of a hot plate, and this one is heated at 90 degrees centigrade. So it is called a soft bake because we usually use a very like not a very small temperature, but a temperature less than the hard baking temperature. And why is it called a pre-bake stage? Because before like even exposing the UV light or the light source, we are baking it before the process, before the patterning process. That's why it is called a soft bake process. And after that, what happens is that, so let's say this PR was a positive PR. Let's say it was a positive PR. Now the next stage is called the exposure stage. So usually what happens is that there is a mask. Let's say it is a bright field mask, and you have a pattern like this, and you are just shining your UV light through this, and based on that, this was your substrate, and on top of that there is this PR as well. Sorry. So there is this PR, and on top of that, the light is shown. And based on the combination of the PR and the mask, so as we have previously discussed, that either the exposed area will be, either this area will be stronger and this will dissolve, either this will be stronger or otherwise it will dissolve. So let's say the created pattern will look something like this. If this is our substrate, on top of that, any kind of a lithography, soft bake is necessary. So you usually need soft bake to remove and settle down the PR. So you are giving us a little bit of temperature to to the PR to be settled down. Even for deep UV and those kind of a things, you will need a soft baking stage. And it also depends on if like like how fine structure are you making and everything. So like if you are let's say if you are moving towards a very fine structure and everything, so you need to optimize these steps. Like even the soft baking stage, the pre-baking and the post-baking and everything needs to be optimized very highly, because based on a little bit temperature, let's say you are giving 95-degree in case of let's say 90-degree, and that will change your overall outcome as well. Uh, Let me check the question. Yeah, so BFM and DFM. Can you tell me the full form of this, Shabana? Okay, so you are saying which one is the best one. So there is no like there is nothing called the best one or the like the better one or something like that. So based on your application, as I was discussing in the previous class as well. So based on your like need and everything, you need to choose this. So based on the majorly in case of R&D sectors like us, so for researchers and everything, you need to consider the cost first. So you need to consider which one costs you less, or like because these masks are also fragile as well. So based on that, you need to consider which one is the cheapest one. And for industry purposes, you need to choose which one is like durable over long time, which one is necessary for your use case as well. So that will also depend on the etching purposes and everything. So the pattern will be something like this for bright field mask and positive PR. And now the necessary step is just a second. Yeah, it happened, right? Yeah. So let me do one thing. Just a second. The pattern will look something like this, not like this. The pattern will look something like this, where you can say that any simulations tool and determine etching rate in 2D and 3D. I'm not entirely sure about this. There might be, but in case of like my research and everything, in general, I use like we generally optimize through multiple times trying. So for the first time, let's say like there are some smaller signs as well. So like if your like etching is not up to the mark and everything, so you need to change your techniques a bit and these things. So it comes with like multiple times trying, and in most of the cases, I'm not entirely sure about this simulation tool or something. So yeah, so it looks something like this, and these will dissolve very easily, and these structures will stay. Now the next stage is called the development stage. Yeah. So development stage. In development stage, what is done is that we have something called the PR developer. So this is like very like intricately connected with the PR we are using. So based on that PR, your developer changes, and after developing or after like just a second, let me draw it a bit. So after few time dipping, sorry, just a second. After few times dipping, or let's say like flowing your developer from the top of your device and everything, the structure will look something like this, and the other parts will dissolve. Now, now the step here comes that is not entirely part of your photolithography process, but you will in general deposit metals and these kind of a things. And let's say we are depositing a metal, right? It's not entirely part of your photolithography step, but metal deposition. Let me remove the number as well. Yeah. So metal deposition. In this, what happens is that you have a substrate like this. On top of that, you have your PR. Let me reduce the other structures. For this case, I'm just showing you this. So this is the red one. Okay. And you are just depositing your metal on top of this. So you have deposited some metal here. You have deposited metal here. You have deposited metal here. Deposited metal here. And you have deposited metal here as well. Okay. Now, what you will do is that, so before this, there is a step, sorry, just a second. Before this, there is a step called hard baking or post baking. In this step, it is exactly similar as the pre-bake. So before exposing your UV, you are in general using the soft baking stage, and after exposing the UV, you are just like hard baking your pattern and everything. So here, let's say you in general heat your substrate with 120 degrees C and 1 minute. So why is it called hard bake? So it is after baking, so it's post baking anyways. And hard baking is because in here we are using more than 100 degrees, so it is 120 degree, and previously we have used 90 degrees. So there's a temperature change as well. So we have increased the temperature in this case as well. So it is called post baking step. And after this, so there will be the metal deposition and these things. So it is also like we are putting our substrate on top of the um, hot plate, and we are heating this for 1 minute. And for different PRs and different labs, and there are several like optimized processes as well. So like in our case, we in general use a 1.5 minute one, and we use 125 degrees. So there are different cases, and based on different PRs and these things. So as I was saying about the metal deposition, so the metal is deposited here. After that, there's a step called, just a second, yeah. So the structure looks like this. So your metal has been deposited on top of the PR and in between the PR as well. So after that, we'll remove the PR. So how this PR is removed? So we'll have a structure like this. So let me draw the previous structure before. So it was something like this and this, right? And you have metal, sorry, metal here, metal here, metal on top of this, metal on top of this, sorry, yeah, metal on top of this. So this was your previous structure. After the removal of PR, what will happen is that is your substrate, and you will have this kind of a structure. Why? Because with the removal of this PR, this part of metal will also be removed. So this is the structure, the intended structure you were trying to make, and based on the mask, based on the PR, and based on the etching techniques and everything, so we'll have ultimately a structure something like this, looking something like this. So these are the like the basic steps of photolithography and the metal deposition and these kind of a thing. So based on your particular need, you will have to deposit metal, or you will have to deposit, let's say, some kind of oxide or something like that. So you have your options even for several techniques like ALD and these things. So if you need to make a pattern with ALD techniques and something, so you will definitely need to use photolithography technique. Can someone let me know why? So let's say So as we know that there are several patterning techniques, so we can use a shadow mask, we can use photolithography and these things. But for ALD patterning and everything, so let's say let us have, I guess I'm just like drawing it here. So we have a structure like this. So this is the top view of the structure. Now we need to make something like this, and on top of that, let's say up until here, you need to deposit hafnium or Al2O3 or something like that, and the rest part is previous. So um, I am saying something like this. So if this is your structure and you need to deposit up to here. So if we are trying to make it through ALD, because we need a very highly uniform and thin hafnium layer, so why do we need to use photolithography in this case as well? So why can't we use a mask or a shadow mask or something like that? Can anyone answer this? You guys can guess as well, right? Just try to guess it. Why is it not possible to like use a shadow mask in these kind of a techniques? Any ideas? At least try to answer it. You can also type in the chat box as well. Think of the basic understanding of ALD before. So ALD creates atom by atom layers, and we are depositing a very ultra thin and a very uniform layer deposition. So why do we need photolithography in this case? So if we need to pattern a very highly uniform and a very ultra thin layer as well. So let me give you a hint first. So based on this mask aligning, so like one of the main step is to align your mask for a photolithography technique. And here based on this gap, so if your, let's say if your substrate, if your mask is here and your substrate is here, so based on that you can also pattern this. And if your mask is directly touching onto your substrate, so based on that you can also, let me write it down, this is your sample, and this one is your mask, and this one is your mask. So based on this, there are two different kind of like photolithography techniques. So these are called the contact and the non-contact mode. So similarly, like different kind of like material calculation techniques like AFM, there are non-contact AFM and contact AFM and these kind of things. So you can think of several kind of issues like shadowing and these things happening in this case. So if I want to pattern ALD deposited film, what will be the best choice to do? Why do we need to use um, we need to use photolithography beforehand to pattern this? At least try to answer this. So if no one is trying, so in ALD what happens is that we have a single atomic layer. So in general, they are 1.12 angstroms. Let's say they are nearly 1 angstrom. So if you are just using, let's say, a shadow mask, even if you are trying to align it onto your substrate and these kind of a things, there will be a space in between, right? There will be a space for air to travel around it and these things. But when you are trying to deposit PR, you are spin coating on top of it, and then you are baking it as well. So even if there is any kind of air bubble or something, that will get removed with these baking processes and everything. And you are doing some pre-cleaning as well, so there won't be any kind of a issue of any kind of a debris or contaminants that will create a layer in between the PR and everything. So your PR and your device will be completely adjacent to each other. So there is a so just a second, let me tell you about this. So even if so for ALD we need to create chemical reactions in between. So if air can pass through it, so a single atomic layer can be deposited on top of this as well. But in case of PR, if there is a PR, so we can deposit this because the reaction sites are only here. So based on this, we can deposit here and here. So this is the basic answer of this question. So there are several kind of etching techniques, micromachining techniques. So that is there is something called a bulk micromachining. And what is a bulk micromachining? So let's say you have deposited this kind of a structure and you need to etch it. So there are several different techniques. So what is a bulk micromachining? So you need to remove this part. So you have already removed this part. This is called a bulk micromachining, and you are removing the bulk material from the whole deposited material. So this is called an isotropic bulk micromachining, where the what do I say where the micromachining happens in all directions and all directions and in a equal rate. And if the and the thing is and if your structure something looks like this, and this kind of a thing is called anisotropic. So there is a complete control of how much material you want to etch away or not. So like how much material or how much or what is the length of the etching that you need to achieve. So that is called an isotropic one, where you have a control over which side to more like let's say, let me describe it a bit. So how to so you need to, let's say, you need to achieve a more depth than a height. So based on that, you can program it that how much micromachining needs to happen. And surface micromachining is that you need to etch away or remove the surface layer. So in between this, there is a very important thing known as the sacrificial layer. So sacrificial layer is a layer we can say from the name itself that it is a sacrificial layer. So a layer to sacrifice. So what happens that if you don't want to, let's say you have a pattern all over the mask itself. So you have a L-shaped pattern like this. So throughout the mask you have this pattern, and on top of your material you don't need to equally distribute this pattern, right? So what you will do is that if this is your substrate or the sample, and you just put a a layer that is known as a sacrificial layer. So what will it do? It will just remove these patterned areas directly, and you will have patterns here onto this substrate. And after that you can just remove this sacrificial layer and you won't have any pattern. So one of the main things we can do with a sacrificial layer is something like this. So let's say you want to make a cantilever. So in a cantilever, if this is your substrate, on top of that you want to create a structure something like this. Okay, so how can you make it? The best way to make it is like, let me just draw it again. So let's say you want to make something like this. Okay, so how will you make it? The best way to make it is through this. Just try to deposit a sacrificial layer, then etch away this part to remove this. So we'll have a slope, something like this. Now your structure will look something like this. Now you will deposit the material on top of this. Just a second. Yeah, so your material will look something like this. And afterwards, you can just remove this sacrificial layer. So if you remove this sacrificial layer, the structure will look something like this. So the structure will look something like this. So this is a very useful way to use a layer that is not a foundational layer that can be sacrificed easily, but it will help you to create this kind of a structure as well. So, and another thing to know is that, so it is a very simple process, right? Photolithography looks very simple and everything, but in most of the cases, you if you need to make a sensor, not a simple one, but like a real time working sensor and everything, so you need several kind of a structures as well. So you need something called multi-stage photolithography. So maybe you need to like pattern the active region as well. You need to pattern the contacts as well, and you need to pattern everything. So you need something called a multi-stage photolithography step. So if there is, so the main point with this is that you are performing photolithography multiple times. So in these cases, your optimization steps becomes very like useful, because if there is a error in the first stage, there will be more error in the second stage, and based on that, the error will increase exponentially. So you need to perform perfect lithography in the first. So if the patterning is very clear in the first stage, if you have a similar mask, so that contains, let's say, two or three different kind of a structures, or two or three different kind of a designs, so you need a multi-stage structure to be made. You need a multi-stage photolithography. So if anyone have any questions, so I am just stopping the lecture part here, and then we'll move towards questions. If anyone have any question, let me know. If there are no questions, I'll move to the question and answer. Okay, so let's move on to the questions, and then if anyone have any question, we'll have some time after these questions as well. So this is the question from the previous lecture that I missed because of the network issues and these things. So first we'll discuss 10 questions from the previous class, and then we'll move towards the questions from the next class, like this class, sorry. So tell me if this statement is true or not. The four basic components of MEMS are microelectronics, micro sensors, micro actuators, and micro structures. So is it true or false? A very simple one. True.
True, sir.
Yeah, so can someone explain it a bit? So, like, as I have already discussed in the previous class, so what are the use cases of each of this, specifically microstructures? Try to answer this. Yeah, that's correct. So, the statement is true. So microelectromechanical sensors are consists of these microelectronics, that is the CPU part of the of a PC, that is similar to a CPU part of a PC. Microsensors, microactuators, sensors senses and actuators actuates, and microstructures are few structures that combines this complete process, and that gives like specific like uh, components that are needed apart from these three structures. So let's move on to the next one. So what does class of a clean room mean? So what does a class of a clean room means? What is a class 1 clean room, class 100, class 200, sorry, class 1000 and these things. So what does a class of a clean room means? Particle count? Not entirely correct. This is correct, but not entirely correct. So anyone wishes to try it? Not entirely particle count. You're half correct, I would say. Anyone? Yeah. So it is the number of particles. That part was true. Indicate the cleanliness level of a controlled environment. Yeah, that's true, but on basis of a quantitative level. Obviously, cleanliness level of a controlled environment and everything, controlled space. But his answer was correct. The particle count part was correct, but that was not entirely true. You would need another few parameters to completely describe what is the class of a clean room. So number of particles, this part was correct.
Per cubic meter of air,
Yeah,
sir.
per cubic feet or per cubic meter. So based on the area you have, so in a cubic feet area, what is the allowed number of particles? So allowed inside the facility or space. So inside the space or inside the clean room, what is the number of allowed particles? That is a particle count, but per cubic feet or per cubic meter and these kind of a thing. So based on these, so there are ISO levels and classes and etc. Now let's move on to the next one. Question number three. So, um, let like let's have this things that there are non-invasive sensors and there are invasive sensors. So, just try to give an example of a non-invasive and an invasive one in your daily life. Then I have the question afterwards. Any sorry, just any example will work. And the invasive one. So try to give an example where in general you use in general you use the same equipment for an invasive part and also a non-invasive one. So something no, first try it, then I'll answer it. Yeah, Dipanjan. So if so, these are the standards, right? So for the clean room, there are several standards. That was first, US gave the basic standard of a clean room establishment that was class 1, 10, 100, 1,000, and these things. So first, this was the standard that is the federal standard. FED means Federal Standard 209E. So this was the basic standard that used to tell you the class of a clean room. Afterwards, it was replaced with the international standards, that was the ISO standards. So try to give an example where you have a non-invasive counterpart and also an invasive counterpart of the same thing. That what do I say? So they serves the the same purpose. So is there anything like that? Let's think of an glucose sensor, right? So you have a non-invasive glucose sensor and an invasive one as well. So you can either either take blood from your take a blood using a syringe from your veins and then test them, and also you can measure them non-invasively as well. But the main thing is that the fall in accuracy and the fall in reliability as well. So if you are, let's say even like with a handheld one and with a lab standard one. So if you are measuring glucose in your home using a lab kit, that the strip kit we usually use. So that one gives let's say you have a sugar the blood sugar level of blood glucose level of, let's say 120, and you might get 128, 124, and even 115 or 110. So there is a less reliability factor associated with this. But with the lab based test, it might be 125 or it might be 115. So there is a plus minus deviation with the actual result. So in case of non-invasive, that is huge. So if, let's say, if your analyte, let's say it should come around 40, but you can have a value of 10 and you can have a value of 70 or 80. So this is the basic thing where you might have a non-invasive one and invasive one. Several other examples can be like VOC sensors that can non-invasively check your blood alcohol level and these things. So in general, in roadsides in roadsides and everything, they use a VOC sensor to check if you are drunk or not. So there are several these sensors as well. They perform very accurately. So these are called VOC sensors, that volatile organic compound sensors. So they measure the blood alcohol or the alcohol like in your exhaled breath. Now let's move on to the next question. Question number 4. Which of the following equipment which of the following equipment is used to maintain the temperature and humidity levels for the appropriate growth and preservation of cell/tissue in a tissue culture or cell culture? So the options are incubator, autoclave, and desiccator. Let me write them down. Incubator, autoclave, and desiccator. Yeah, which one is it? And also let me know what the others do as well. Yeah, incubator is fine. So what are the what the other devices or equipments do? What does the autoclave do and what does the desiccator do? Autoclave, just a second, let me check the text. Boiling the particles before deposition. So autoclave, exactly what is an autoclave? So the first or the primary thing autoclave does is that, yeah, perfect. So it is a high pressure and a high temperature steam chamber where you in general sterilize your lab equipments, medical tools, and these kind of a things. And based on that, there can be you can also give a very high temperature at a very high pressure, and you can make several kind of materials out of it. So many material researchers also use autoclave for these kind of purposes as well. But the main work of an autoclave is maintaining your device equipment or your materials in a very high pressure and a high temperature region. And what does the desiccator do then? What is the basic work of a desiccator? Yeah, transport, store, and protect the materials from humidity. So in general, that the devices, the fabricated devices may get disturbed with the contaminants like dust, humidity, pressure, temperature, and these kind of things. And based on that, the device performance may change. And so to keep these in a safe place before characterization, before transporting them to another lab or something like that, so we use a desiccator. So yes, incubator was the right one. Now let's move on to the next one. Which kind of a microscope is generally used for observing cells and organisms in petri dishes, flasks, or microplates, or let's say in a culture or something like that. So, which kind of a microscope is used? So, your options are stereo microscopes, metallurgical microscope, and inverted microscope. And also tell me about the other two as well. So which one is the correct one? Yes, inverted. So we need an inverted microscope to check the cell cultures and organisms in petri dish flasks and these things. So what are the other two best for? So what does a stereo microscope do? Anyone have any idea? So what is it used for and everything? So a stereo microscope is the common microscope we generally use. So that is a um, in biological samples and those things as well. So for samples like you need to check under a directly to magnify the that thing. So you need an optical microscope that is called as a stereo microscope. And basically, if you are checking your sample for any kind of a cracks, if you are checking any kind of a like a larger thing, yeah, that is the correct one. So that is a three-dimensional view of the specimen. And what does a metallurgical one do then? A very similar thing, but what does it do? It's very similar. You need to just check for the surface cracks and these kind of things. So you need a higher magnification. So that is called a metallurgical microscope. Nothing but that. So let's move on to the next one. So that was question number five, right? Question number six. Sensor for VOC detection, TCOs such as ITO, tin oxide. ITO is indium tin oxide, and ITO, ZNO, or that is your zinc oxide, etc., were used as sensing material. What is TCO? VOC is volatile organic compounds, and for this, what is TCO? So for volatile organic compound detection, that is for gas sensing in general. So you need ITO, tin oxide, zinc oxide, and these kind of a things. So what is a TCO? What do you mean by TCO? So the first option is, let me give you the options then. Thin conducting oxides, two thin, yeah, coating oxides, or transparent conducting oxides. And the answer is transparent conducting oxides. So let's move on to the next one. Question number seven. So what is a difference between piezoelectric and piezoresistive and piezoelectric sensors? So what is the basic difference between these two? So what do you mean by a piezoelectric and what do you mean by a piezoresistive one? So are they same or not? So that's the first question. And if they are different, so what is the basic difference between them? Which one is easier to interface? Which one is harder to interface? Then like which one have a different kind of a mechanism and these things. So let me just give you this. The first point needs to be if they are different or not. Are they different? The next question is that um, which one is easier to interface and why do you think so, obviously? And third, the working principle. So the first question is obviously they are different. Yes, different. The first one is obviously yes. So which one is easier to interface and why do you think so? Piezoelectric is pressure to voltage and pressure to resistance. Okay, and others? The working principle is that for piezoresistive, based on the applied force or the pressure, based on the applied force or the pressure, there is a change in resistance, and we are measuring that. And for piezoelectric, based on the applied force, there is a change in charge accumulation. So ideally it can be a voltage one or you can measure it through currents as well. So but the basic thing is that there is a charge accumulation based on the force and based on the force there's a change in resistance. So which one do you think is easier to interface? Which one is easier to interface in your opinion? Piezoelectric. Okay. Others? Just tell me a sentence of why do you think so so I can understand your like thought process. So which one do you think? Others? So which one is easier to measure? Think about it. So is it easier to measure the change in resistance or is it easier to measure the change in voltage or current and these things? Yes. That's the point. So that's why it is easier to interface a piezoelectric sensor because like the change in voltage or the change in current is easier to measure and easier to measure not only measure but also accurately measure as well. So in case of resistance, it is easier to measure, but the accuracy of the device is also under question. And in case of a very accurate answer, you need something called LCR meter or a resistance one. So like because of that, like it is easier to interface a piezoelectric sensor. Now let's move on to the next one. Question number 8. So we have a resistive sensors are one of the most widely used sensors. What will happen? What will happen with the resistivity of metals slash semiconductors when temperature is increased. So resistive sensors are one of the most widely used sensors. So what happens when we increase the temperature in case of metals and semiconductors? So do they increase the resistance or do they decrease the resistance? What happens if we increase the temperature of metal and semiconductors? Increases resistance. In which case? Or in both of them? So you are saying that for the both of them, the resistance increases for metals. Yes, that's true. For metals, resistance increases, and for semiconductors, the resistance decreases because there will be a better conduction as well. So for semiconductors, the resistance decreases, and for the metals, the resistance increases. Now, so like let's stop here for the previous classes lectures, and now we'll move on to today's questions. So let us start with question number one again. So with respect to a clean room, with respect to a clean room, what do we mean by PPE? What does PPE means? So you all I guess everybody knows about the PPE kits and these things. So what does a PPE means? So there are three options. The first one is personal protocol equipment. The second one is protective protocol equipment, and the third one is personal protective equipment. Personal protective equipment, yes. So in COVID times and at those times, like doctors and the health workers were wearing a PPE kit. These were known as a personal protective equipment. So they are not only for their protection, but those were also for the protection of the others. So for avoiding any kind of a cross contamination and these kind of a things. Now move on to the next one. So let me know, is it a true or a false statement? During So I guess everybody has already saw this video demonstration of impedance analyzer. So in that, the demonstrator has like discussed about true probe and four probe. So which one is the better one and why? So which one is the better process, a two probe or a four probe one, and why is it a better one? So which one is the better process? The two probe one or the four probe one? And I have a follow-up question as well. Everybody has seen the videos, right? It's a very simple answer. The answer was four probe obviously. But why? Main question was why. Why four probe is better than two probe? And what do you think about if I increase the number of probes? Let's say from four I am increasing it to eight. So will there be increase in the accuracy or like it will perform better? So I need a comment on that. Try to answer it. You don't need to be entirely correct. Just try to answer. Anybody wishes to try it? Yeah. So the answer is that obviously a four probe system is always better than two probe, and similar to that, a eight probe system is also better than the four probe. But now the thing arises that we need a certain amount of accuracy increase, that we are creating a very complex circuitry. So with the improvement from the 2 probe to 4 probe, the accuracy increase was high, but with the increment of this 8 probe to 4 probe, the increment was not that high. So with this much accuracy increase, you may not wish to use a more costlier and a more complex equipment. Also, there is another thing that with 8 probe we can have other capabilities as well. So based on your use case and based on your need, you might need to use a 8 probe or a 6 probe and these kind of a things. But the basic thing of a 2 probe is that from one axis, from one probe, you are providing an electrical current, and from the other one, you are receiving the current back. And now you are just measuring the voltage from each of these probes, and you are determining the impedance. Now for the four probe system, there is something like this. So you are sending an electrical current, a small amount of electrical current, and you are receiving that electrical current, but you have another two probes where you are measuring the voltage, and it gives you a better estimate of the resistance because there is contact resistance involved in these cases, and because of this there will be a field, and then the voltage measurement through the other two probes will help you to improve this accuracy. Now let's move on to the next one. So in photolithography, we can bake the sorry we can pre-bake the sample at 50 degrees centigrade. So can we bake the sample at 50 degrees centigrade? Why not? In the demonstrations we have used a 90 degree. Yeah. Why not? Like, why can't we use a reduced temperature? Let's say 50 or 60. Yeah, both of you are correct, right? So 90 degree is necessary, but why can't we use a 50-degree temperature? My question is that. And why 90 degree, or let's say 95, 100 degree is more suitable for these cases? Yes, it might leave residue. That's the correct one, because most of the photoresist is dissolved in solvents that have a much higher boiling temperature and much higher evaporation temperature. So because of that, what happens is that it might leave residue, even if some of the parts are removed, but you need at least 80, 90 degree to remove most of the this thing. And because of this, a problem arises that is known as the wet baking, where even with the baking procedure and everything, the substrate may be left with some wetness, and because of that it may destroy the mask as well. So you need to perform a baking process at a much higher temperature, but not as high as a post baking temperature, but it needs to be a much higher temperature than 50, obviously. Let's move on to the next one. So which among the following can be used to fabricate microheaters? First one is SiO2, second one is NiCr, and third one is diamond. Which one is correct? Yes, NiCr. Can anyone tell me why NiCr? Why NiCr is suitable for it? Good conductor of heat. Let's move on to the next one. Question number 5. So which among the following is a PR stripper? First is ethanol, alcohol, or you can say IPA, isopropyl alcohol. Third one is acetone, and fourth one is BHF, acetone. Yes, that's correct. Let's move on to the next one. So in DRIE, that is deep reactive ion etching, enables very low aspect ratio etches to be performed into the silicon substrate. So is it true or false? DRIE, that is deep reactive ion etching. False. Yes, it is false. Oops, sorry, false. Now move on to the next one. Question number 7. In which type of etching the etch rate is dependent on crystallographic orientation of the substrate? So in which type of etching technique is dependent on the crystallographic orientation of the substrate. So if you are using a different kind of a substrate, the etch rate will be completely different. So in which kind of a etching technique, or let's say a wet etching technique, let me maybe mention it here. In which kind of a wet etching technique the etch rate is dependent on the crystallographic orientation? Yes, anisotropic. That's correct. So let's end it here. But for here, so why do you think, here I had a follow-up question, I missed that. So why do you think ethanol, IPA, BHF won't be able to strip PR? And also, if they can, so why are not we using that? And what is the use cases as well? So for ethanol, what is the use case of that? And for alcohol, what is the use case of that? And for BHF, what is the use case of that? So my question is that what is the use case of ethanol, IPA, BHF, and what are they best used for? So let me give you a brief. So ethanol and IPA both are very mild alcohols, so they are best for using as cleaning agents for cleaning, while BHF is a very hard substance that can be used for etching, even for etching processes of SiO2. So it may even remove the desired layer as well. So based on that, so you need to strip your PR, not to destroy the other deposited layers and everything. So you need to use uh, you need to use a like a solvent that is potent enough, but also not destroy the other layers like the SiO2 layer or something like that. So that's why we need to use acetone. So let's end it here. Thank you for attending today's session. So thank you for attending today's session. If anybody has any question, you can ask me right now. Okay. Thank you.